Hello, this is Mr. Garcia. I'm going to be showing you how to graph a regression line and calculate the coefficient of determination, the r squared. And once we have the r squared, we can also calculate the correlation coefficient, just r. So I've got a couple of data sets here. One is the speed that a car is traveling. The other is the corresponding braking distance. In other words, how far it would take in feet to bring the car to a complete stop. So for example, you can see that if I'm traveling at 15 miles per hour, it took 44 feet to bring the car to a complete stop. On the other hand, traveling at 75 miles an hour, it took 433 feet to bring the car to a complete stop. So we're going to begin by selecting our data, because we need to tell the computer what data we want to use. And so I'm going to just click on the 15 and drag it all the way across my data like that, and then just release. Okay, and then I'm going to insert, because I want to make a graph out of this. I want to make a scatter plot, right? So I'm going to insert, then come over here to charts, and I'm going to choose scatter plots. I'm going to choose the first one that will work for us. All right, and there's a beautiful scatter plot of our data. Down here we have speed, and along the y-axis we have braking distance. Notice that braking distance is the response variable, and the speed is the explanatory variable, right? The speed explains the braking distance, doesn't it? Okay, it's because I'm traveling faster and faster that it takes longer and longer to bring the car to a complete stop. All right, and as you can see, the scatter plot looks very linear. It has a very strong positive association. So I would guess that the correlation coefficient is very, very close to 1 here. And so now we can just actually see the exact numbers. So we're going to click on this plus here, and I want a trend line, and you can see that it already graphed one there for us, but I'm going to go a little further and get the equation of that linear regression line. So I'm going to click on the little arrow here to get a drop down menu, and then I actually want to come all the way down here to more options, and I get this nice dialog box that comes up. Okay, so I can switch here to an exponential regression line. We'll be doing that very soon. And then we can also do a polynomial. We'll be doing that one as well. So, but what I really want to do now is come up with the equation of this regression line. So I'm going to keep it on linear, and I'm just going to scroll down, and here I can see display equation on chart. So I'm going to click that, and there's my equation. And then I'm also going to I want to display the r squared, the coefficient of determination. So I'm going to click on that. All right, and that's pretty much it. So now we're going to just interpret this data here. So the first thing we should look at is the equation. Notice that the y-intercept is -77. That means if we were to extend this line all the way down here, it would crash into the y-axis down here at -77, right? That's the y-intercept. The slope, on the other hand, tells me the what? The change in braking distance divided by the change in speed. All right, and so really we could the denominator of that, let's call it just 6.5 roughly. So the denominator of that is 1, right? So every time the speed changes by 1 mile per hour, the braking distance is going to change by approximately 6.5 feet. All right, so every 1 mile an hour increase in speed correlates to a 6.5 foot increase in braking distance. So that's how you interpret that linear regression equation. And then the r squared, well, that tells you about why the braking distance, or the y values, are changing, right? So there's some. These are varying, aren't they? It goes from 44 to 433. If there was no variability here, if they were not varying, they would all be exactly the same number, right? But the braking distance, right, depends on the speed. So we would expect, right? And when this is exactly what happens, that the braking distance varies, right? It changes depending on the speed of the car, all right? And so, but this braking distance is not exactly correlated to the speed, right? There's a little bit of randomness built in there, right? What could be some of the things that are causing this, right? It could be the reaction time of the driver. It could be the quality of the tires, right? The tires might have changed, right? It could be the pavement might have changed. The temperature increases or decreases, okay? There could be small little variations like that that we can't really account for, right? But, and as a matter of fact, you can actually see that on the graph, right? If this were exactly, if the braking distance were tied exactly to the speed, then these points should lie exactly on this line, but they don't. So this one's a little above, this one's a little below, this one's a little above. So there's something else going on here, right? There's something else is causing these braking distances to vary, all right? But you can see they almost lie on this line. So most of the reason that they're changing is because of the speed of the car is changing. But there's also a little bit of randomness built in there. And so what this R squared measures is the percent of the variability that is due to the changing speed of the car, right? So there's basically two reasons why these vary. It's the speed of the car changing and its randomness, okay? And so the percent of the variability, or why these are changing, that is due to the speed is 98, right, and about 98.5%. The other 1.5%, okay, is due to randomness. So that's how you interpret that number. And if we wanted to find the correlation coefficient, then we would just simply take the square root of R squared, and I happen to have a calculator here, and if I do that, I get 0.992, which is almost 1, right? So it's very, very high correlation coefficient, and that tells us the strength and direction of the linear association between speed of car and braking distance. So 0.99, what was it? 0.992 is very close to 1, right? So that's a very strong linear association, and since it's positive, it's telling us that basically as one variable increases, the other variable will increase, and that's exactly what's going on here. All right, so thank you very much.